We start the session, sir.
All right. Thank you very much.
Yeah, okay.
Uh,
I'll just give an introduction and then hand over to you, sir.
right.
Oh, okay. Good morning to
Good
all of
morning.
you. Good evening and good afternoon for participants joining from different geographies. Okay, we will start the parallel session, second day today. So for this session, I would like to introduce our chair and co-chair. Engineer Ravi Sundaram will be chairing this session. Engineer Ravi Sundaram is a postgraduate in geotechnical engineering from IIT Delhi. He has over 40 years of experience in site investigations, pile foundations, and ground improvement. His international experience include offshore soil investigation and offshore driven piles. He started his career with McClelland International USA and worked on the company's projects in Saudi Arabia and Qatar. He has published over 65 technical papers that reflect his experience in geotechnical engineering practice. He was chairman IGS Delhi chapter during the period 2009 to 11 and is currently the executive committee member of Indian Geotechnical Society. On behalf of the organizing committee, a warm welcome to you, sir.
Thank you very much. Thank you.
We also have Dr. Rajiv Sarkar as the co-chair of the session. Dr. Rajiv Sarkar is an assistant professor in the engineering department at IIT ISM Dhanbad. He's obtained his PhD from Indian Institute of Technology, Roorkee, in 2009. Dr. Sarkar's area of interest includes soil structure interaction, liquefaction of soils, ground improvement, and discrete element method. He has published more than 30 research papers in reputed international, national journals and conferences. Welcome you, Dr. Rajiv Sarkar, on behalf of the organizing committee as a co-chair
Thank
for
you
this
very
session.
much. Thank you.
So with this, I will hand over the session to chair and co-chair to manage further. Over to you, sir.
Thank you very much, Dr. Parthasarthi. It's a great opportunity to participate in this international conference and also be the chair for this technical session. Uh, without taking much of your time, I will invite Dr. Ashish Juneja to make his presentation. It's really a great honor for us that Dr. Juneja from IIT Bombay is going to be talking on disturbance in soil structure interaction due to post-cyclic recompression. Now I hand over the session to the co-chairman, Dr. Rajiv, for his initial remarks, and then Dr. Ashish can start his presentation.
Okay, let me start with the Professor Juneja's brief bio. That Professor Juneja is a professor in the Department of Civil Engineering at IIT Bombay from 2005. He has more than 70 publications with over 300 citations from various national and international journals and conferences. He received his PhD in Geotechnical Engineering in the year 2002 from National University of Singapore, Singapore. He has twice received the Excellence in Teaching Award in the year 2012 and 2016, besides Best Paper Awards by IGS and other geotechnical agencies. Professor Juneja has served as a consultant to agencies such as Indian Railways, NHSRCL, NPCIL, Mumbai Metro and Nagpur Metro, BMC, Samsung Engineering, John De Null and John Deere. The project for Konkan Railways resulted in him being awarded the 2014 IIT Bombay Industrial Impact Award. With this, I like to hand over the session to Professor Juneja for the presentation of his special lecture on uh, on disturbance in soil structure due to post-cyclic recompression. Thank you, sir. Over to you, sir.
Yeah, thank you, Professor Sarkar. It is indeed an honor to be invited in this prestigious conference, and And to be honest, it seems the way it has been planned and the way the background images appear as if we are in the conference venue. And if you happen to zoom in, you can actually take the first row seat, which, right in the first row seat of the conference hall. Okay, with this, I like to, spend the next 15 to 20 minutes to just to tell what we have recently, done something in our laboratory and, examine what really, what happens to soil after they are subjected to numerous cycles of loading. The genesis of this, in fact, comes from the figure on the right-hand side. What you see is the railway embankment. Some of you may recall that quite a few years back, the then railway, the honorable railway minister had overnight increased the axle load of the, the train, the track, the load on the railway tracks. If I remember, I think from 2021 ton, it was jumped to right to 25 ton or so, maybe more. But you can pull out those figures. But this tremendous jump, overnight jump, was done without giving a scientific thought to it. And lo, all the embankments they perform successfully. So in a way, there has to be a certain background to it, that the soils which have been subjected to cyclic loads from the railways. So as an example, you see the high frequency loads which have come from the railway track, the wagons and the engine, especially the engine as well. So these have because of this subjection to these loads, the soils below have over the period, undergone deformation. As a result, their bearing capacity or the strength have improved. So we are looking at what soils, the improvement, and at least to quantify those numbers. So this is a work by Dr. Muhammad during his PhD. Aslam, he's now he's very well established, and I'm grateful. So all these slides which are present are in fact from his PhD work. Okay. So to give you a brief background, what really we mean by, when the soils are subjected and what happens. If you look at an ordinary triaxial test, the figure on the left-hand side shows the same sample. I mean, the same soil with the same void ratio, but one is subjected to a higher, confining stress. The other one is subjected to lower confining stress. So lower confining stress, common sense tells us it'll show us a hump and a drop. A higher confining stress will be more like irrespective it's clay or sand, it'll show you like a normally consolidated soil, something like that. So to understand these two figures, look at the compression space which is on your right hand side. Both A and B have similar void ratio, but because they lie on either side of the ultimate line or the critical state line, you see that the sample A or the soil A will compress and soil B will dilate. Now, it means it's important to understand that the soil from these curves is not only nonlinear, plastic, but is also stress dependent. This stress dependency is something which we like to examine in the next 10-15 minutes. Now, if you look at an ordinary Moore Coulomb or even those Cam Clay kind of models, what you see is look at this E log P curve, your standard E log P curve. What you see is if I'm on the URL unloading reloading line, can I just make this mouse thing as a second, please? I'm just trying to make this as a pointer. Okay.
Right click, yeah. Thanks.
So if you look at the unloading reloading line, so both Moore Coulomb or those Cam Clay family of models, they'll tell you no matter you go millions of times on this line, you'll just retrace this every time, you'll retrace this path. So the same thing happens when you do multiple, loading, unloading. So it's just a replicate of that figure. The same, and if you look at the stress space, starting from A, going up to B, and if I unload B to B and then reload it, like my, any kind of dynamic load I apply, it just goes up and down with no change in any additional strains occurring, and no new development of shear volumetric strains being developed. Okay. However, what you see is if I have multiple load cycles which are going at a certain period of time, what you see is the pore pressure development in the first cycle, and then in the second cycle and third cycle, it's not the same each time. You do see a different response which is more like a real life scenario. So the bottom line is you do need a kind of something like a slightly more sophisticated soil model to understand this phenomena which occurs. And of course, I'd like to just give a brief background on what happens to soil during loading. During loading, majority of you would be knowing you can either have a flow type failure, meaning loose sand or normally consolidated soil. They're quite nice up to a certain number of sites, and then bang, it fails. Dense deposits will have more like cyclic, wherein the mobility, wherein the deformation increases, and this would first and second case are more serious. The third one is where if you have, for example, the soil is still trying to accumulate a lot of plastic strains, and it does not really reach its ultimate state. It just continues to take in more load. So we'll concentrate, in fact, more on first and the second type, because if you look at it, these are the soils which are really studied for liquefaction studies. And also we look at the third one, because these are the ones which actually interest us for long-term stability of embankment, which is the case here. So the contents of my next 15 minutes are going to be, I'm going to present something on what are the stress pore pressure changes in soil when the soil is subjected to a lot of cycle loads. Try to present some degradation model similar to your structured soil model. So very simple model. Of course, there are quite complex models, but as we understand, because of the limited data available, a lot of those recent models which have been developed, it's really very hard to comprehend because of the number of input parameters. And also speak about what happens in the post drainage, whether it's intermediate or post drainage. And briefly, if we get time, to comment on this observed changes in soil structure. So we have three kind of soil samples which we used. One is two are the sands. That's the first and the last column. What you see is the sands are the first sand is more like rounded. It's like rounded particles, and the last one is more like angular particles. We also use silt size particle, which is way more like subangular to angular. So, and all these soils were shown to lie within the potentially liquefiable, deposits. The routine lab tests were done, so this is pretty much routine. One additional thing which I like to highlight over here is the kind of sample preparation method. So sands are normally, either prepared by, pluvator. That's the preferred method for us. So I like to speak about pluvator. Although for silty deposits, I think we went on for under compaction method, which which is routinely followed. But I like to look at the pluvator which we have in our laboratory, and which we try to model using DEM. So that's a simple a single soil particle. If you look at it, maybe at 1 second it's somewhere here. And it falls down and then rebounds. But I like you to look at the graph which is on the left. So at 1 second, it's still somewhere, it's not moving. That's 1 second, it's still there. At 1.5 seconds, that's the vertical line, it starts to drop. So 1.5 seconds, it drops. At about 1.78 seconds, it hits the perforated plate. So that's the first break happens. It's just like a break, it breaks the energy. So that's where the first 1.78 seconds you see is some kind of elastic rebound happening. and then thereafter at 2.1 seconds or so, it drops to the inside the container, and wherein its velocity all of a sudden becomes not zero, but because of this energetic layer, there is some up and down rebound of the particle which happens. Now this energetic layer controls your quality of your sample. Okay, there's been a lot of work done, and we are also trying to give a little bit input to it. What you see is the energetic layer plays an important role, at least in the quality of the sample. Please look at the small figure, if you can see at the bottom, and I hope you have the front row seat by front row seat by zooming in onto the PPT presentation. What you see is, the sample quality which has more like a variable height diffuser. This is what we normally would like to advise. The diffuser should be able to go up, move up as the particles get filled up in the container. Obviously, because you want the constant height of fall, but you're fixing the first perforated plate, or the first plate which actually helps break the larger size, I won't say lumps, because this is all granular particle, but it does not allow the soil to fall in lumpy kind of manner. So the other one, which is more like static, you see there is difference in the void ratio. So these small values, of course, will play whenever we need to explain some kind of background. These do help in understanding that why my soil has behaved in such a way. But having said that, what you see is the ultimate state. That means the friction angle at its ultimate state. That's the first figure. Irrespective of what kind of sample preparation method you have used, or the figure on the right, which shows other critical state parameters from compression space, it means that the constant volume failure, or the failure at which happens at ultimate state, those conditions do not change irrespective of what kind of sample preparation method you use. But having said that, there is, for dynamic loading, there is a substantial difference. If you compare the figures on the left and right, the moist time sample, if you really take a hand lens and look at them carefully, they give you less number of cycles to reach liquefaction compared to the pluviated samples. Pluviated samples are about, if you look at those numbers, they are a bit, but notably higher. So this, in fact, we always say pluviated samples replicate more of a natural kind of deposit. So these are typical, cyclic loading curves, and let's not go into that. It's typical standard. One additional thing is what we noticed was the excess pore pressure ratio when we plot against the number of cycles. So if I take one single test in something like 1,000 cycle or maybe 10,000 cycles, so blue line shows a single test going straight away, and the grayish kind of line shows the same, similar soil sample, but this time it undergoes in thousands, in this case, hundreds of cycles. The right side is thousands of cycles. And after each 1,000 cycle or so, it's allowed to drain and then start the undrained loading again. Obviously, this excess pore pressure ratio on the vertical axis does not do justice to it, because it doesn't show a drop and the drop. But we have broken down each and every channel of the 10 cyclic loading, 10 sets of cyclic loading, and then added them up. So again, excuse me, the vertical axis, it probably should not be compared to those figures on the left hand side. But what we see is the triaxial test results, irrespective of whether we went stepwise or one single go of maybe 10,000 cycles or more, the test results seem to suggest that the stress strain response is quite similar. So this led us to the very basic the degradation parameter, the development. Which is really, I think it's more than for 30 years old. I think Ni et al, they have used it probably a couple of decades back, and A number of, so that's a degradation parameter similar to for your structured clay. What it's seen is that if I introduce this, can I just develop or use this degradation parameter in terms of, I think this is Z times eta, so that's Z. Probably what you see is, yes, if I plot the number of cycles to failure and try to get a relationship between the degradation parameter, I do get some kind of very obvious relationship. Even the figure on the right hand side will help us that this is cyclic stress, but I can also use, it's a CSR, so I can, because all the samples in this case were tested to I think the starting confining pressure were quite similar, I think 100 kP or so. So what you see is you can develop some relationship, and let's see with this relationship, are we able to, curve fit it? So that's what engineers are happy with it. What you see is with very large number of cycles, maybe about 100,000 or so, you cannot, there is large difference. Although with less cycles of up to 100, it gets a good really fit. Obviously, because you're trying to combine connect the two ends of the curve. Like it's not the whole curve, so two ends are being connected. But for majority of the tests wherein the number of cycles are large, it's difficult to connect. So even over here, what you see is so this degradation parameter is not helpful. There are other models, power model, which have to curve fit parameters A and B, and you can do this. So idea is you trace, how do you trace this pore pressure ratio, excess pore pressure ratio against N. But again, this has limitation because you still are not able to connect. So we can there are hyperbolic models again with two unknowns, and with the development of more curve fitting platforms. As student or we can sit down and get endless fits, but none of them give any theoretical background to what really happens. So in last couple of decades, you will see a lot of papers which have come out, but there's no theoretical background. Of course, they use a lot of less computation. They come at a lot less computational cost, and they are simple. What we would like to see is something wherein you can, at least the soil performance can tell us, it is not only the pore pressure response, but also whether we can see whether the strains and stresses, they also are able to, tell us something more about the performance of the soil. So that figure on the top left is something which tells us how the model, we have just said, it can go up and down. But now in this case, what we have done is, that's what do you call it, stable boundary surface, which is shown. And if I start the soil loading from point A over here, after when the unloading starts, it reaches another value of it reaches another elastic leaf of A2. So somewhere it starts to load, and it's still inside the it reaches the elastic leaf, which is still inside. So if we can somehow adjust the hardening parameter, which is given by this line over here, NCL. So some of you may be familiar with hardening parameter like P naught prime, and we bring in some kind of again a degradation theta as we have brought in, but this time we are trying to adjust the hardening parameter in such a way that it reduces the size of the yield surface each time you do a cyclic loading. So somehow my new P prime value or P naught prime value is less than the starting. So let me say, if this figure, if I have this over here, and after loading, it starts to understand a new P naught prime. And with this new P naught prime, if I load it, it will go to a different set of, again, it'll start to give me a different performance in terms of pore pressure response, in terms of effective mean stress, etc. So these equations on the right are not there to scare you. I apologize, but if some of you understand that elastic, these are your Hooke's law relationship, but the plastic strains which we use are typically from, these are associated flow rules. And I mean, the idea is to look at whether we can have a degradation parameter this time, which can adjust the pre-consolidation pressure. So this is what we have done.
Sorry to interrupt, sir. Sir, it is almost 15 to 20 minutes is
Okay.
over.
I'll just take another 2 minutes if it's all right.
Okay, sir.
Yeah.
Okay, sir.
Okay, thank you. So this degradation parameter, as we said, it's like it varies from 0 to 1. 0 would mean your typical Moore Coulomb or Campley, and 1 would mean that your hardening parameter is made to change. So I'll just skip through some of the additional slides. I'm sorry, it's just I think. Let me go to the next one. I'll go to directly to what is the final one. So apologize. Yes. So the final one is with the adjustment against the number of the hardening parameter, we are able to model the response of the soil with only two additional unknowns. Two additional unknowns, and this is the beauty of this simple model. I'll skip this. Yes. So after the the cyclic loading is over, we are looking at what is the volumetric strain in the sample against the pore pressure response. So the volumetric strain is your change in void ratio over 1 plus void ratio. That's the horizontal axis. What you see is with samples which have high pore pressure ratio and less pore pressure ratio, you can still string the data along a single line. But it's interesting to see what really happens to these. This is probably the last thing which I like to highlight in this is with samples which have RU less than 0.75. So you can take it as a magic number, but what you see is the unloading reloading line, which is shown by black arrows over here. It doesn't make much of a difference. The property of the URL or the kappa, as we say, is the same. But with RU more than 0.75, what we see is there is a change in the slope of the unloading reloading line, meaning the structure of the soil is changed when your pore pressure response is high. And in fact, these numbers can, just to give you some, these numbers can vary anything from 2 to 4. So your gradient of your unloading reloading line is large. I'll again yeah, this is, so again with this background, can we now predict what is the increase in strength? So Q star is your new strength divided by old strength. So that's undrained deviatoric strength increase divided by the old one. And that's your OCR. So that's OCR by definition. So if you look at the paper, the definition of OCR is slightly defined over there, how OCR we have taken. But are you less than 0.75, you still see that the performance of the silty or the angular sample is better compared to the rounded granular deposits. And if I have RU more than 0.75, that is when the sample really the pore pressure response is higher. What we see is the increase in strength, okay, is kind of seems to be independent of your CSR. That's again an interesting thing, but again, it has a relationship between OCR over here and the power which we have OCR to the power of some kind of capital lambda over here, capital lambda over here. This capital lambda, our work has shown, can be obtained even from your standard triaxial test. Meaning, if I need to find the strength of the soil, the increase in strength of the soil due to dynamic loading, I really do not need any cyclic triaxial test. I do my routine triaxial testing, that is my drained and undrained triaxial, get my capital lambda from there, and I can see I can predict what is my increase in strength. And in this case, it shows the increase in stiffness.
Dr. Juneja, may I request you? Yeah, okay.
Yeah, with this, I'll just conclude the presentation that the post-cyclic characteristics of the soil are dependent on the pore pressure accumulation function, which is again based on numerous work. You can work over it. And of course, we have given some hint on the particle size and shape, which makes some effect on the performance on the response. Okay, with this, I'm sorry I took additional, I think, 5 minutes. I'm really grateful to the chairman and vice chairman for allowing me to speak. Thank you.
Dr. Juneja, it was a very interesting presentation. That is what prompted me to, give you as much time to speak. I wish we had the opportunity of listening to you some more, but definitely I think there will be in the future. Thank you very much for your very vivid presentation. Now I
Thank you.
request Dr. Rajiv Sarkar to, uh, uh, ask for the questions, and then we can move further.
I can wait up to the end for the questions if you want. I'll stay up to the end of the session.
No problem. If I had one small question.
Please.
Have you been able to apply these principles on any specific project sites to see how, actually what happens after liquefaction, the post earthquake response, or something like that?
No, not yet. But
Okay,
we have only seen non-liquefiable soils. We have more like concentrated on those kind of thing, which we have not reached liquefaction stage, because I think more like data is very limited for liquefied soils. So we were more onto the performance of soils which are just under routine machine foundation loads or railway loads.
So you have applied these on such kind of applications in the field, is it?
No, not in the field.
Maybe in the laboratory some tests have been done?
We have only done some numerical studies, simulations. That is the limitation.
I think there is a lot of potential for application and to real life situations. I look forward to seeing more research from you on this subject, because this is something which is really of very great interest. What happens after liquefaction? People only talk about whether the soil will liquefy or not liquefy, and then if it is not going to liquefy, everybody thinks it's a very happy situation, and you move ahead.
Agreed.
Not sure if Dr. Rajiv Sarkar is here.
I think he just lost his connection, sir. He's joining in a minute.
Okay. I think we can move on to the other presenters. I understand Mayank Majumdar is not presenting today.
Yeah, yes, sir. He is not there. Just sent a message. I think his colleague was trying. I think he is not able to access. You can leave that and adjust those timings, sir. And two more presenters are yet to join. So we will just let them know if there are any connection issues. We are trying to resolve that. So Majumdar will not be presenting. Two more will yet to join.
Okay, so Devbrata Ghosh is there?
I think he is there.
Okay, Mr. Devbrata Ghosh. Yeah, welcome to present your behavior of low height embankments on soft clay under seismic conditions. So what I have been conveyed is that you are allowed 8 minutes. So please try to stick to that time. Thank you very much, Devbrata.
Good morning, everyone, to the respected chairperson and co-chairperson, our keynote speaker, other esteemed delegates, and other esteemed presenters. My name is Devbrata Ghosh. I am from Civil Engineering Department, Pore University. I am here about to present the topic behavior of low height embankment on soft clay under seismic condition. I have done this research under the guidance of Dr. Indra, Assistant Professor, and Dr. R.B. Shaw, Professor of Civil Engineering Department, Pore University. So let's begin with the presentation. Here is a brief overview of the whole presentation. We'll start with the introduction, followed by methodology of analysis, result and discussion, conclusion, and conclude with the references I have used for this study. Introduction. Embankment is a very common civil structure used for different purpose like site control, transport, irrigation, and depending upon its construction material or its purpose, it can be categorized under earthen embankment, rock fill embankment, railway or roadway embankment. It has huge effect on livelihood, and its sudden failure that happens in case of seismic event can cause a lot of damage to the property as well as the human lives. These are the main forces that is engaged normally in case of embankment failure. The gravitational slippage, sudden drawdown, seismic forces, artificial hazard. Our primary concern in this presentation will be the seismic forces. Now, low height embankment normally in our country is constructed for rural or suburban transportation purpose, and it is normally checked against the static stability, but very few times or low budget or other constraints, it has been checked against the dynamic loading. But it's in recent times it has shown that the due to low to moderate level earthquake, this can be causes of the failure of those embankments. So a thorough analysis of this type of embankment with foundation soil in static and dynamic condition, with in association with different monitoring of different parameters like core pressure, vertical deformation, lateral deformation is very necessary. Methodology. A numeric modeling has been done using the finite difference software FLAC, and a full scale model of the embankment in association with the subsoil condition has been developed, and basically a parametric study has been performed with the variation of its embankment height, its soft layer thickness, and other engineering properties of the soil construction material. And for dynamic loading, the representative low operator earthquake has been taken, but as it
Hello,
quite high PJ.
Yeah, tell me.
You continue. Arya, can you please mute the other participant, please?
The low operator earthquake has been a quite high PGA, so it has been scaled down the in respect of PGA to simulate some input motion to intended PGA values. Now this is the geometry of the embankment. The face width has been 10 meter with quite stable static slope, 1 vertical is to 2 horizontal, and soft layer thickness has been varied 5 meter and 10 meter, and the all below soft layer there is a stiff clay layer. Its shear velocity or proper as well as shear modulus has been changed, and all combination leads to the 12 number of different models. These are the assumption of the analysis. Initially, this has been assumed free from any sustained shear stress. Water table has been at the bottom of embankment. Slippage is not considered as in transportation way. It is commonly not encountered. One stage embankment is allowed and consideration is not allowed. Plain strain mode has been adopted and mode column constitutive model has been adopted for this analysis. This is an flow diagram of the sequence of the analysis. In table 1, the geometric properties of the 12 models has been shown, and as well as in table 2, the engineering properties of the soil material has been tabulated. Now this is the representative low operator earthquake that has been taken as a reference, and these are the power spectrum showing this frequency range mostly within significant frequencies mostly within 20 Hz frequency. And these are the original acceleration time history that has been derived from the original low operator earthquake with PGA 0.07, 0.15, 0.25 G that has been used in the dynamic analysis of the model. And this has been the displacement uncorrected baseline corrected and uncorrected displacement history. The time history has been baseline corrected. It has been the shear stress, shear time history has been put at the base of the model for analysis, and the boundary has been taken as non-reflecting boundary. Either it means the wave reflection back to the model won't affect the result, as if the wave would not be reflected back into the model. The mesh generation, for mesh generation, the mesh size has been kept in association with the study of fluent manner Lismar, and 1/10 of the shortest wavelength in associated with the significant maximum frequency range, and it's turned to be in our case the maximum rectangular element is of size 0.5 meter cross 0.5 meter. Result and discussion. Results and discussion has been categorized before proceeding to the dynamic analysis. Static stability has been checked. Now in table 4, the instantaneous settlement has been tabulated, as we are not considering the consolidation here. The vertical settlement is not very much in different cases for 5 meter and mainly affected by the soft layer thickness. Or like in case of 5 meter embankment height, the soft layer thickness is for 10 meter, the vertical settlement ranges from 20 to 23, and for 5 meter soft layer thickness, it has been very less, 4.5 to 7 meter, and static factor of safety ranges from 1 to 6.128 depending upon the model. It suggests quite static stable slope, and this is the under static condition, the pore pressure distribution before and after embankment construction. And you can see the after embankment construction, there is a rise in pore pressure, and as the clay material for low permeability is not able to dissipate. Now, for acceleration amplification case, the acceleration amplification has been shown in all the cases. The blue line shows the original input at the base, and the saffron line shows the best acceleration, horizontal acceleration time history. And for model 1, as an example, is shown for all 3 PGs, and this shows the acceleration amplification happens in all the cases. This is the acceleration amplification variation with the height measured from the base level of 3 models. The from blue line suggests the lower PGA level, and gray line suggests the higher PGA level. And for some of the acceleration amplification behavior, this amplification versus input PGA curve for different model has been derived, has been plotted, and one similar pattern has been shown for all cases, that with increased PGA, the acceleration amplification tends to decrease. This observation and the amplification majorly happens in soft layer, and the amplification decreases with the increment of input PG. This is the observation. The vertical settlement is another important parameter as it is related to the serviceability, and it has been derived in the undamped and damped cases for all the models. And it has been shown in this table. And as a summary, we can from the table saw the vertical phase settlement is more in undamped cases than in undamped cases due to shear modulus degradation, and it has been tabulated in the plot for mid-phase settlement versus PGA graphs for both types of embankment. And the discussion is that the settlement pattern variation with the PGA is most dependent upon the soft layer thickness and also varies with the embankment height. And PGA is the major affecting factor of the settlement. With soft layer thickness, the increase from 5 to 10 meter, the settlement is increased 2.5 to 3.5 times. And the major vertical settlement are restricted to the soft layer and embankment layer. That has, we can see from this contour diagram. So vertical settlement, horizontal displacement regarding from this contour diagram, we can see that as opposed to the vertical settlement, it mainly happens in the soft layer below the toe level.
Like, your time is up.
Yes, sir. Plus, this 2 minutes, sir.
Okay.
The toe in toe region, as of in case of vertical settlement, we have seen it is maximum in the crest level and below crest level. So this is the difference from our vertical settlement pattern and horizontal settlement pattern, and this pattern is prevalent for all the model that has been shown for model 1 for 3 PGs and model 4 and 3 PGs. Now this and the horizontal displacement of toe of the embankment model in the against the PGA different PGA level and different models has been shown in the curves. And here is the pore. Normally we are dealing with the clay, so the excess pore pressure distribution or liquefaction phenomenon should not happen in our case. So for a cross section, we have calculated the pore pressure distribution after and before the dynamic loading and excess pore pressure generation due to the dynamic loading. That has been shown in the bottommost contour. Excess pore pressure generation for model 1 or against 0.25 G. And excess pore pressure generation is less important. The more important parameter is excess pore pressure ratio. And for model 1, we have seen 0.07 G and 0.15 G, 0.25 G. The pore pressure ratio is maximum in the soft layer, that has been shown by the green patches here. And but it is well below the 1, that is the value for the causing instability. The conclusions: the all chosen model exhibit the factor of safety greater than 1, suggests a quite static stable slope. The crest amplification with respect to the base decreases with the increase of PG, and major portion of amplification takes place in soft layer. The modulus degradation in damp cases. Vertical settlement mainly is only dependent upon the PGA of import motion and soft layer thickness below it. The horizontal displacement is maximum near the soft layer in the below the toe level, and sustained excess pore pressure ratio maximum is soft layer, but its not enough to cause any instability from excess pore pressure point of view. These are the references I have used for my study. Thank you all for your presence.
Thank you, Devbrata.
Yes, sir.
Now, I request Dr. Rajiv Sarkar, are there any questions? You can take it over. So thank you, Devbrata. Then there is no question from the audience. So we now move on to the next presentation. Is Rohini Kollapalli there in the audience?
I think she is not joined, sir. And the Tanay also is not there. Both of them are not there. They're yet to join. You can move to the next one. Yeah, both of them not there.
Okay.
Yeah.
So we have Adesha
Yes, sir, I'm
Swayamsiddha.
present.
Amanta.
Hello, am I audible,
Yeah.
sir?
Oh, yes, you are.
Okay.
Did I pronounce your name correctly, Adesha?
No, it's Adyasha.
Adyasha. Okay.
Yes.
Thank you, Adyasha.
Good morning, everyone. I'm going to present on the topic investigation of seismic response, dynamic response of rubber tire chips for geotechnical engineering applications. So, from the very topic name itself, the first question that comes to our mind is that what are these rubber tire chips and why are we talking about the application of these tire chips in our geotechnical engineering application? So for that, first we need to know what are scrap tires. So here you can see, this look like any ordinary tires that we see in our day-to-day life, be it your car tire, be it your scooty tire, be it the tire that we see in the trucks. But these are the tire which are discarded because they cannot serve the original purpose for which actually we have bought them. So what to do with these tires? These tires are either should be dumped in some landfills, but these tires have self-ignition potential, as a result of which just dumping them in any of the landfill can be very problematic. Hence, many countries started dumping them in the open grounds. Again, they become the breeding places for mosquitoes and rodents, which is again problematic for the community health. So these tires have many useful properties, like they are very lightweight, and they have, unlike other ways, they are very durable and long lasting, and they have good insulation potential. So rather than getting them dumped anywhere and throwing them as in waste, these can be recycled and reused for different purposes. So as a civil engineer, we can contribute by using these materials in our civil engineering practices. And these materials are also being used in chemical and petroleum industry for different purposes. So coming to the civil engineering applications, according to ASTM D6270, these materials are divided. Their derivatives are divided under three heads. They are tire crumbs, tire strips, and tire shreds. The division is made basically based on their sizes. So the tire derivative, which are greater than 5 centimeter, are called tire shreds. Tire chips are the derivatives in between 1 to 5 centimeter, and the smallest one, that is lesser than 1 centimeter, we call them tire crumbs. So again, if you have ever observed a tire properly, you might have seen that there are reinforcement in it to provide strength to the tires. So what about the reinforcement? So basically, tire shreds being the largest in size, we do not expect any reinforcement to be removed from the tires after cutting them into smaller pieces. But in tire chips, we do expect the removal of metal reinforcement or wire reinforcement that is present. And in case of tire crumbs being the smallest, we do not expect any kind of we do not expect any kind of reinforcement present in them, be it metal or be it fiber reinforcement. So now coming to their uses in civil engineering field. In geotechnical engineering field, the first use started reported in the year of 1990s, and mainly in the countries of US and Canada. And the pioneering research was reported by Humphrey in 1998. Later on, it spread it to the area of Asia Pacific region and Europe. And in Japan, they started practically using these materials around 2000s. And there are many questions about the use of these materials, like if they will affect the environment, and if they will affect the health of the public. So though all those critics were silenced by Professor Edel of US in 2007, and after that, these materials showed a tremendous use in civil engineering field. So these materials are being used as a filling material in embankment. As I said, they are very lightweight. They have a good drainage permeability, so they are used as drainage material at many places. And now coming to the material used in the present study. So we have used tire chips. These are the basic properties of tire chips and sand that we have used. The sand used in the present study is Indian Standard Sand Grade 2, and the tire chip used in the present study is cut from a locally available scrap tire. So the experimental program for the present study is we have conducted strain controlled undrained cyclic triaxial test for 3 different confining pressure, 7 different strain amplitude at a frequency of 1 Hz, and for total number of 42 experiments were carried out at a relative density of 60%. So coming to the experimental results, here we can see that these graph shows deviatric stress versus number of loading cycles. So here we can see that the deviatric stress initially to maintain a shear strain of 0.15%, we can see there the deviatric stress is very high for sand, but gradually as the loading cycle progresses, we can see there is a vast decrease in the or deterioration in the deviatric stress value. And at the end, we can see a particular small band. This is because our cyclic triaxial machine has an external load cell. For that, we have a small band of this deviatric stress. But ideally, it can, if we have a submersible load cell, then these value reaches 0 on the initiation of liquefaction. Okay, but when we compare the result of sand to that of tire chips, though initially tire chips has taken very less deviatric stress to maintain the equal or the similar level of strain, but you can see that initially here for sand, for the all the condition being similar, the sand started degrading for initial 20 cycles, and later on the sand reached liquefaction at around hardly 60 to 90 cycles. But if you go for tire chip, you can see that the band is maintained constant, like with the even after 1500 number of loading cycle, unlike sand here I have just applied some 150 number of loading cycle, even the loading cycle is 10 times higher than that of sand. We can see there is not much degradation in the deviatric stress that it was taking initially to the deviatric stress that it was taking after 1500 number of loading cycle. So coming to the mean effective stress, a similar kind of behavior as seen for deviatric stress, we can see initially for sand, the stress was very high and later on it reached 0 towards liquefaction, but that is not seen in tire chips. Now coming to the excess pore pressure ratio. Excess pore pressure ratio is generally used to define the initiation of liquefaction. When the value reaches 1, we say that liquefaction has happened. So here we can see, in case of sand, the liquefaction happened at around 60 to 70 cycles. But here in case of TC, here you can see hardly the value reached 0.07, which is like very less, very lesser than that of this than that of 1, the value 1. So here we can see that the tire chips have a great potentials toward liquefaction, and the pore pressure ratio generation is not seen or is very less in tire chips. Now coming to the effect of strain amplitude. So we can see the damping ratio increases with strain amplitude and the shear modulus decreases with strain amplitude, and the similar kind of behavior is seen for both sand and tire chips. If the effect of confining pressure is also similar in both the materials, we can see that as the confining pressure increases, the material becomes more stronger because of the lateral confinement, and we can see the damping ratio decreases with increasing confining pressure, and the shear modulus increases with the increasing confining pressure. Then coming to the effect of the loading cycles on shear modulus. So here we can see this x-axis shows the shear modulus and this y-axis shows the number of loading cycles. For sand, you can see that the shear modulus degrade very fast. Like for initial 20 cycles, we can see that the shear modulus degraded for sand. But if we see the shear modulus value of tire chip, it maintained a lower value, I agree. But that value is maintained constant with the increasing number of loading cycles. There is no degradation as in case of sand. Similar
to time is up, Adhyasha. Please finish up.
Okay, sir, just 1 minute. Yeah. So similar behavior is seen in damping ratio as well. And coming to the shear modulus value, so the tire chip have a very lower shear modulus value in comparison to the sand, but a very high damping ratio value in comparison to the sand. And these are the number of loading cycle. You can see the maximum number of loading cycle for the lowest strain amplitude chosen was around 800 per sand, but the excess pore pressure ratio value didn't even reach 0.1 after 1500 number of loading cycle for tire chips. So this is the conclusion. The main key conclusion is that the tire chip have very high damping ratio but low shear modulus. The typical trend is similar for both sand and tire chips. And the stiffness degradation with cycle is not seen in tire chips, which is very prominent for the initial cycle in sand. And TC tire chips are the material which are very resistant toward the excess pore pressure generation. So these are my conclusions. Thank you. Sorry, references. Thank you.
Thank you very much, Dhyasha. That was a very interesting presentation. Dr. Rajiv Sarkar, you have any questions, please?
If anybody is having any queries, they can ask Adhyasha. And or if I have a small query, Adhyasha.
Yes, sir.
What's the size of the tire chips you have used?
So the tire chip size was 12 mm cross 12 mm, and the thickness of the tire chip was varying, subjected that the tires that we get from the market are subjected to wear and tear. So we have a varied thickness in that way.
Okay.
But, yeah.
Okay. Well, okay. And have you?
Yes, I have one small question.
Yes, sir.
What are the field applications? Where do you feel that can it be used on roads for?
So these materials have a vast application in the field. And of course, directly, if I want to use just the tire chips in the field, that will be problematic because they undergo high compression and they have low strength. But if I can potentially mix them with sand, it can gain strength from the sand, and also it will possess the damping behavior from the tire chip. These composite material can do magics in the field. It can be used for vibration reduction, be it in pavements, be it in railway embankments. It can be used as lightweight and cheap backfills in the retaining walls. And it can be used as drainage layers in the landfill. Actually, the application is not much widespread here in our country, but it is being used in the countries like Japan, practically in the field. So yes, they are very useful for the field.
So what is suppose I was to use it for a road embankment or a railway embankment?
Yes.
Do you think it will enhance the life of the road or the embankment? You have any?
If we are talking about the these materials are not decomposed with time. So based on the durability, yes, it will work for a long year. Means like just like sand, it can work for many years. And additionally, it can provide the vibration mitigation property to the embankments, to the nearby areas. So if we talk about the railway embankments or road embankments, then these are very useful as we are getting cyclic load from the top.
Does the CBR value have any effect?
I have not studied it yet, sir. But I feel, and I'm not saying that to use this material completely throughout the embankment, but yes, a considerable portion, it can be placed as in layers.
But you don't have any thing of what should be the thickness or how to design it.
So that is my present study now. I am carrying out numerical investigations on that, and I hope soon I will report something on that.
Thank you very much. Thank you. Very interesting.
Thank you.
Sir, one question from the audience in the Q&A section. How is the excess pore pressure ratio is calculated? Is it similar to UBCS sand model? Adhyasha, can you respond to this query?
Sir, the excess pore pressure ratio, I have done cyclic triaxial tests. So I have a pore pressure transducer and I measure the pore pressure that is getting generated. And after that, it is divided by the confining pressure. So you get the pore pressure ratio. And when it reaches 1, we call that it is liquefied.
Okay, I hope Harsha has got the answer. Okay. Sir, shall we go to next presentation?
Yes, I think we should welcome the next presenter. Who is the person? Abir Sarkar, is that? I think he is in the audience here.
Yes, sir. Hello, sir.
Oh, hello, Abir.
Yeah.
So, numerical study on vibration screening using trench filled and sand from rubber mixture. So, this is a similar
Yes, sir.
presentation. Look forward to hearing you, Abir.
Okay, so I'll be presenting on a numerical investigation wherein we are using a sand crumb rubber mixture for mitigation of ground-borne vibrations. So let's go through a brief overview of the presentation. The presentation has been arranged in 5 parts. Initially the introduction, then followed by the problem statement, then the methodology where we will be discussing about the material properties and the finite element analysis that we have carried out in Praxis. That will be followed by the results and finally a few conclusions on the study. So about the ground-bound vibrations. So one of the major problems in soil dynamics and also what we are facing nowadays is the vibrations, is how to mitigate the vibrations that is being generated either from machine foundations or maybe from train loading or maybe from any transport vehicles. So these things are affecting the nearby structures. So this is a very hot topic right now. That how to contain or how to isolate this such type of vibrations. So from initially one of the few most popular techniques is through trench barriers, and one of them is open trench and then is infill trench. These two types of trench barriers has been studied by researchers over the years, and one of the most successful initial studies was reported in 1968 by Woods. Thereafter, several experimental investigations and numerical investigations have been carried out. Numerical investigations has shown a great potential due to because a lot of parametric studies can be conducted. So what we are going through, one of the most established facts is that the acoustic impedance ratio of a material, it controls how fast the waves can travel through a particular material, right? So, so if a trench material that we are giving, if it has a low acoustic impedance ratio, then definitely it will be able to screen the vibrations. One of the factors how we are going to evaluate the efficiency of the vibration screening is through calculating the ARF, that is called the amplitude reduction factor. The amplitude reduction factor, it is calculated by taking the ratio of the vertical displacement amplitudes when there is a change and when there is no change. And finally, the efficiency can be calculated as 1 minus ARF times 100%. So it gives the efficiency in terms of percentage. Few of the studies that we have consulted in the earlier, and you can see that the number of the types of infill materials that have been studied. Concrete filled trench material has been studied. Geofoam filled trench material has been studied widely. Then also intermittent geofoam, where there are alternating layers of geofoam and air pockets. Has been studied, but there are few studies which have reported on sand and rubber mixture. So in our present study, our main focus is on utilizing this sand and rubber mixture. One of the few reasons is, as already discussed by Yadasha ma'am, the importance of crumb rubber or the importance of rubber. So one of the big issues for the open trench condition is that there can be an issue of wall instability if there is an open trench, and also that it can get filled with rainwater, which reduces its efficiency. This was suggested by Algen in 2015, and so therefore an infill trench condition is a safer solution. Crumb rubber is basically a waste product, as has been discussed previously, so it is very cheaply available, and also it is a non-biodegradable, so it's difficult to dispose. So utilization of crumb rubber would also be an environmentally friendly approach, eco-friendly approach. So that is the main motivation of the present study, to use crumb rubber, and also the objective of the present study is to evaluate the screening efficiency of the sand rubber mixture as an infill material. Let's start with the problem statement. So this is the schematic diagram of the numerical model, and over here from the sectional view we can see that over here we have given a sinusoidal input loading. Here is the loading, and followed by a change, and apart from that, then we're going to measure the pickups, the vertical displacements at certain intervals. This is the sectional view, and this is the top view. Coming to the material properties, we have we need a soil box for the modeling, And we have taken the local soil properties at NIT Center campus for modeling soil box. For the dynamic modulus, for the dynamic properties of the soil, we have referred Alpin to 1970, this paper. Followed by then the sand crumb rubber mixture. For modeling the sand crumb rubber mixture, we have taken locally available Barak River sand and also locally available crumb rubber from the local industries, and we have performed numerous resonant column tests to determine the shear modulus, to determine the shear wave velocity, and from the shear wave velocity, ultimately we get the dynamic shear wave, the shear modulus G. G is equals to rho Vs square. So from RCA test we get the Vs, and then from the relation G is equals to rho Vs square, we get the G values. The SCR mixture was prepared in 10, 20, 30, 40, 50, and 70% crumb rubber mixtures, and also at 35 and 65% relative densities. The material properties, the soil properties are here. These are the soil properties. Some of the tests, the shear wave velocity and the primary wave velocity were determined from mass flow test and seismic refraction tests. These are the SCR properties. It can be seen that earlier we have talked about the acoustic impedance ratio. So we saw that the acoustic impedance ratio is lower for the 35% relative density. So that's why we do not do any tests considering the 65% RD, because acoustic impedance ratio of 35% RD is lesser, so it should give a better result. These are the dynamic properties of the SCR mixture at 35% RD. We did not consider the 65% RD. Next, the finite element analysis. The study was carried out with 1/4 of the total geometry, and the exciting frequency of the loading was kept at 10 Hz. Also, we have changed the loading frequency further to see the effect of the exciting frequency. The physical damping has been caused. It was assumed to be relic damping, and the relic damping parameters of alpha and beta, they were determined for the different materials. This is the machining and the modeling of the FEA. This was done in Plaxis 3D, and obviously absorbent boundaries were used. For the validation, we have compared the results of the present study with the previous studies, and it was found that we have a fairly consistent results. Coming to the result section, this is the vertical displacement variation of the OT and IFT at the nearest. This is at the nearest point, and this is at the farthest point. So we can see that this is the black line is for the without change condition. The minimum obviously we found for the open change condition, because open change has the highest efficiency, and followed by there was the infill change condition. This is the same at the farthest point as well. About talking about the effect of the change depth, the change depth is probably the most important criteria for a change design. As we can see that with increase in the change depth, the ARF is decreasing. So the ARF is decreasing. That means the efficiency of the trench is increasing. The effect of the distance of the pickup point as we move further away from the pickup point, or as we move further away from the source of the source of the vibration, we can see that there is a decrease in the ARF, suggesting that there is an increase in the efficiency. Then we have the effect of the exciting frequency. We have seen that we have varied up to 40 Hz of frequency, and we have seen that as we increase the frequency, the overall effectiveness of the system is increasing. So initially at 10 Hz, we had a higher ARF, and as we go on increasing the frequency, we see that a dip in the ARF, suggesting that there is a higher efficiency of the change performance. This is the same for both OT and IFT conditions. And finally, we have the effect of the percentage of the crumb rubber in the SCR mixture. We can see that as we increase the percentage of the crumb rubber, the ARF decreases, which means that the efficiency is increasing of the change as we are increasing the crumb rubber. However, with an increase in the crumb rubber, it definitely means that obviously it means that there is a better damping effect, but also it also suggests that there is a reduction in the strength of the soil. So a balance must be maintained. Coming to the conclusions. In case of the open change, we found that 80 to 90% efficiency was observed at the nearest pickup point for the normalized depth of 1 and width of 0.05 and at a length and the change being located at a length of at a distance of 0.4. For the case of IFT, about 50 to 60% efficiency was observed under the same conditions. And this was for the loading case of 10 Hz frequency. In the next one, the present analysis also shows that the error decreases with an increase in the frequency. So we will suggest using the sand crumble mixture for higher loading frequency, not for lower frequencies. And lastly, as we suggested that increasing the turnover, the efficiency of the trench was increasing. But however, the load carrying capacity of the soil also decreases because as we keep on increasing the crumb rubber percentage in a sand crumb rubber mixture, the shear modulus it decreases and the damping ratio increases. So a decrease in the shear modulus it would imply that there is that the stiffness of the material is decreasing. So therefore, the load carrying capacity of the mixture is also decreasing. So therefore, while designing a particular balance should be maintained so that the load carrying capacity of the soil is also there. That's it. These are some of the references that we've used.
Thank you very much. That was an interesting presentation. Dr. Abir, would you like to, sorry, Dr. Rajiv Sarkar,
Yes.
you can take over.
Yeah. Dr. Abir, it's a nice presentation, and
Yes,
just if the audiences have some query, they can ask Dr. Abir. Or else, I have few queries. Can
yes,
I
sir.
ask Dr. Abir?
Yes, sir.
Please, sir, please.
Yeah. Actually, how was the loading pattern in your finite element model?
How was the loading pattern?
The loading
It was
pattern.
a sinusoidal. It was a harmonic loading was considered.
Is it from the top or is it from the bottom?
No, it's from the top. Once I'll show you. Over here is a dynamic source. At this point, we have designed it for 1/4 of the model. So at this point, there was a dynamic source.
Actually, that's my doubt. Actually, why 1/4 of the model?
So 1/4 of the model, sir, so that the computational load is less on the system. Otherwise, since this is a 3D model,
you may have asymmetric in the other axis. Generally, if you are having plasticity or the nonlinearity, then we used to go for the half model.
Yes, sir.
1/4 model, the reasoning or the reasoning for 1/4 model is not clear to me actually.
Okay, sir, we did the 1/4 model in order to save the computation time. That's it.
Yes, but have you tried it with any model with half model and compare it with the 1/4 model?
So we haven't
Any
done
trial
it
or
in a half
something like that?
We haven't done it, but we have actually recently we have conducted another study, but it was done in Abacus, and that was done in an axis symmetric model, a 2D. It was a 2D model. So
it was. Yes, sorry. It was a 3-dimensional model, and
yes,
that's why, and it's a non-linear model, right?
Yes.
So in that case, you can check it with whether your 1/4 model is able to replicate the full phenomena.
Okay.
Check it out. This is my
okay. We'll check it out.
suggestion or advice, you can say.
Okay, sir.
Yes.
Okay, so we'll check it out once.
Yeah.
There is one question in the chat box.
Yes,
which
sir.
material model is being used in Plaxis? Asked by Adyasha.
Which material model? I'm sorry, the question is not clear.
Which material model is being used in Plaxis? Adyasha, if you would
May
like
I
to
ask the
clarify.
question directly?
Yes, sir. Yes, sir.
Yeah, I'm just asking, what is the constitutive model that you have used to replicate the behavior of these materials?
Ma'am, we are actually using we have actually assumed the material to be a linear model. Actually the main problem is that or rather why we are assuming it to be a linear model is that this is a low strain condition. So in low strain cases we have that it almost follows a linear stress strain curve. It's only a problem when we are going for the higher strain conditions, then we have a problem. But in the low strain, we have modeled it as a linear material.
Okay, so it is linear elastic.
Yeah, linear elastic. Yeah.
Okay, thank you.
Okay, in that case, your 1/4 model is maybe suitable. If it is a
Sorry?
if it is a linear elastic material,
Yes,
then
sir.
your 1/4 model may be suitable.
Why it is suitable?
No, no. I heard that you have used the
Yes,
linear elastic
linear
material.
elastic.
So if it is a linear elastic material, then your 1/4 model may be suitable.
Okay.
I was assuming that your material is non-linear plastic.
No, sir. Well, we have assumed a linearly and elastic material.
Then how did you consider the effect of rubber tire chips?
As in,
The model?
are you asking about the damping characteristics?
No. I am asking that how did you model the rubber tire chips?
So we have the basic properties of the rubber tire chips, the shear modulus, and also we have also the classes already calculates the damping parameters, the daily damping parameters.
Okay. Okay. Ravi sir, if you have any query?
No, thank you. I think some questions which I had in my mind, you have already asked. So thank you very much, Abir, for your presentation.
Yes, sir. Thank you, sir.
I think are any of the other presenters in the audience, or we do not have any of the other speakers?
I think the others have not joined, sir. Two of them. One person has messaged they are not present. The other two, we are unable to contact them. So they are not joined. So we can conclude.
So before I conclude, then I'd like to invite Dr. Ashish Jineja, if you have any remarks.
This is, I mean, I want for you in a remark regarding the conclusion of the session.
Yeah, regarding the papers presented.
Yes.
And anything which you would like to add on your own presentation?
I actually...
Just because we have the time, so I thought we can utilize it effectively.
Yes, very correct. So the thing is, I really like what Chairman has asked, because the practical implication of all the presentations today is something pretty important, and we should focus on that when we start to do any kind of experimental or theoretical work. And given the level of expertise in the different, the experiments and the numerical simulations which have been, presented today, I feel that, we have done pretty well, at least in terms of the, the knowledge, or in terms of the equipment, in terms of the expertise of all the presenters today. So I enjoyed all the presentations, all the three presentations which I saw them today. I think there were three, and to be this the presentation by I.I.Sc is in fact known because I am her RPC member, Research Progress Committee member.
Okay.
So I was glad that to really hear her and see her. The other presentations were very nice. So I'm only now regretting that if I had those 5 extra minutes or 3 extra minutes at the beginning, I would have also done justice to what I wanted to say.
I appreciate what you're saying and apologize. I hope that we will get further opportunities to listen to you. Actually, myself, I being a practical field person, I always try to look for how these can be applied in the field, and that's what excites me. So, in fact, even whatever questions I asked were all related to how can I go and put this on the ground. That is the main thrust, which I feel academia, industry, if that energy transfer is there, I don't know about technology transfer, then there will be a lot of real life problems going to the research, and research being applied in the field. I think that's how we should move ahead. I think then geotechnical engineering, we would have done justice to it.
This is very, very true, because I think what we should also be looking at is also on the same lines as having a kind of a steering committee. So when the research aspects of any research project is developed, along with the progress committee members, which are again from the academia, we should have members from the industry as part of the steering committee, because they are the real people who actually know whether this such a project, how far its implementation will be possible in the field. Because we they and to a larger scale, I mean, of course, when I say implementation means extend the whole thing to a bigger and larger scale. So I very much appreciate and like this, and maybe in the very near future, whenever we have a research progress committee coming up, I would definitely recommend that members from the at least one or two member from the industry, experienced member, they should be part of the steering committee.
That would be very good.
Mhm.
Dr. Partha, you have anything to add?
Yeah, I was very curious to ask one question. When we are migrating from natural materials to these man-made materials, for like these rubbers and other things, so what will be the long-term performance, sir, over the period of time? Because it has never been tested so far. And the same thing also holds good for, say, concrete, for example. So when I built my own house, we did some concrete cube test. 28 days, the strength was not achieved. But, using some fly ash, over a period of 56 days, the strength actually got maybe 70% more. So that seems to be very curious. What will be the long-term effect of these man-made materials compared to the natural materials? And there are a lot of research is going on in this front as well.
I agree with you that we need to see the long-term effects. The fly ash mixed concrete you pointed out. There has to, there can be some accelerated tests done in the laboratory, which can tell you that whether the life of the building is going to be 70 years or 50 years or 100 years, whatever. That will help. And of course, these rubber tire and other materials which are being researched, if we could have test tracks or some such this thing to see how the performance is, somebody has to come forward and be bold enough to implement it. Because right now I see what is written in the IS code, I can't go beyond that. So that becomes quite challenging to even measure up to what is not written in the IS code. How can we just test it and bring it, of course, into the codes if possible.
In fact, in one of the programs D.N. Singh had conducted in IIT Bombay, he called so many people to have some research ideas. I think I was also on, and this topic has been raised by some people there, that we are depleting with the natural materials when the man-made materials is evolving things. So how we evaluate the long-term performance and how confidence we can implement those things in the application per se.
See, the whole problem comes that if these materials, somebody has to take that risk that even if it fails, they have to be ready to bear the cost and move forward. But till that happens, I think in our country we are into that fault finding mode, that whose fault it was, and there is no end to it. Thank you very much. I think we have had a useful discussion, and I now hand over the session to Dr. Parthasarthi. But before that, I'd like Dr. Rajiv to add any final closing remarks.
Actually, sir, I like to regret for my network problem, because actually I'm not in my institute. I had to rush for some family emergency problem in Kolkata, and now actually Kolkata is raining. In Kolkata it is raining, so I had connection problem. Anyway, I learned a lot from this session, especially Professor Juneja's lecture. Actually, I was the person who stopped Professor Juneja, but anyway, I'm sorry for that. And anyway, other three presentations were very good. I hope we learn from the presentations and come up with some technology which may be implemented in the practice. Thank you. Thank you. I now hand over the session to the chairman, sir.
Right, Dr. Parthasarthi, please
Yeah.
take over.
Yeah, thank you, sir. Thank you, chair, and thank you, co-chair, for very nicely managing the sessions. So we had three presenters not coming to the session. We could have extended the time to the other presenters. So we really apologize for that, because I was just missed Professor Ashish lecture. It was so interesting on the experimental investigations, talking to those presenters who are absent. But I will have another opportunity to listen to him in full. So anyway, as usual, it was a very nice presentation from Professor, and also the other three presenters were extremely enlightful, and there are a lot of informations on the research works. Really appreciate that. So on behalf of the organizing committee, I really thank the presenters and the special lecturer, Professor Ashish Juneja, and the chairman and the co-chairman as well, to manage the session successfully. Thank you very much, sir. We can actually conclude this session.
Thank you.
Thank you very much.
Thank you.
It's been a
Thank
great
you.
pleasure.